Hello, my name is Ashwath Saravanan. I am an 11th grader at Northwood High School in Irvine, California, and my project is a smaller scale of energy harvesting and lighting systems through piezoelectric tiles. The problem that inspired me to do this project is that America's society must advance towards energy harvesting techniques like piezoelectricity due to our electrical power grid facing a serious reliability crisis as more people continue to using it, causing a lot more variable risks. America's electrical power grid is facing a significant increase in demand, which the North American Electric Reliability Corporation warns may exceed generation capacity over the next decade. This rising demand, compounded by risks like severe weather, cyber attacks, and pollution, highlights the urgent need for innovative solutions to improve the reliability of the power infrastructure. One promising approach is energy harvesting, which captures energy from the environment to convert it into usable electrical power. A notable method is piezoelectricity, where certain materials generate an electric charge in response to mechanical stress. The effect occurs due to the asymmetric arrangement of atoms in piezoelectric materials. When subjected to pressure or vibration, the internal polarization of these atoms shift, creating a measurable electric charge across the material. Researchers have successfully embedded piezoelectric materials in road surfaces to harness energy from moving vehicles, powering traffic lights. However, applying piezoelectric energy harvesting for indoor lighting systems remains largely unexplored, despite lighting being a major contributor to electric consumption. The study aims to develop a small-scale piezoelectric energy harvesting device to power indoor lighting. The project will use an Arduino to convert the weight applied to a piezoelectric tile into an output charge displayed on an LCD. If sufficient voltage, up to 5 volts, is generated, it will light up a small LED. While research constraints limit the scale of the project, its core concept remains feasible. This project investigates energy harvesting using piezoelectric tiles, which generates a small voltage from mechanical stress, primarily vibrations. The key components include the piezoelectric tile, a boost converter module, and an electrolytic capacitor. The circuit stores and converts weak charges into readable voltage for the Arduino, powering an LED when sufficient voltage is available. An LCD displays the harvested energy and voltage levels. The Arduino code facilitates control and data visualization through three main functions: acquiring the voltage data, visualizing this data on the LCD using the liquid crystal library on Arduino IDE, and checking if the voltage meets the threshold of 2.5 volts to power up the LED. There are many materials that were used in this project, but the three main ones that were crucial to the functionality of the device was the piezoelectric disc, which converts pressure into tiny bursts of electricity, an electrolytic capacitor at 470 UF and 16 volts, which stores harvested energy in order to smooth voltage fluctuations, and a boost converter module with an adjustable output voltage, which increases the harvested voltage to power the LED. On the right, there are pictures of these crucial components. And on the top right, the cost of materials needed to make one device is about $56, making this project affordable. A brief overview of the procedure is step one, component research, which is here I researched the components needed and found their data sheets. Step two is breadboard layer and grounding, where I connected the ground pin from the microcontroller onto the breadboard, thus setting the breadboard up ready for a component connection. Step three is component connection, where I use the knowledge gained from component research and connect the components to their respective pins on the microcontroller through the breadboard. The fourth is code development, where based on the functionalities mentioned earlier, I write code on Arduino IDE that satisfies the functionalities needed for the device. Step 5 is testing and calibration, where I use a multimeter to check if the voltage going in the device and out are same and safe for usage, thus making sure there's no electrical issues. I conducted two experiments with the following research question and hypothesis. My research question was, how do mass and displacement of a weight applied to a piezoelectric tile affect the voltage produced? My hypothesis to this was, as weight increases, the voltage produced will also increase. As the weight moves further away from the center of the tile, the voltage produced will decrease. In the first experiment, I tested the voltage generated by a piezoelectric tile with different dumbbell weights: 5 pounds, 10 pounds, and 15 pounds. The weight was placed in the center of the tile. The Arduino was powered, and the voltage was recorded onto the LCD display. Each weight was tested three times, and the averages and standard deviations were calculated for analysis. The second experiment examined how the displacement of a fixed 10-pound weight from the tile's center affected voltage production. The weights were placed at distances of 2 centimeters, 4 centimeters, and 6 centimeters away from the center of the tile. Similar to the first experiment, 3 trials were conducted, and the averages and standard deviations were calculated for visual representation. This is a quick demonstration of my prototype device.
Hi, I am going to give a quick time demonstration of how my project. Over here, we have the device that I built for this research experiment with this piezoelectric tile connected to the breadboard circuit that is being powered on by this Arduino microcontroller. The microcontroller then has a USB cable that connects to a laptop where the code for Arduino IDE is present. I'll first start off by plugging in the USB cable and uploading the code. And right now it's stabilizing, and I'm about to put this 15-pound dumbbell on top of the piezo disc in the tile like this. See, as we can see, there's a 3.6 volts being produced from the dumbbell, and the LED light is switched on.
The first experiment confirmed my hypothesis that heavier weights induce more charge, showing a direct relationship between the weight applied and the produced voltage. Figures 4 and 7 support this claim as it shows the table and bar graphs of my recorded data respectfully, and showing how each dumbbell weight increased as the voltage output also increased. I observed that the device stabilized before delivering the voltage and heated up with the dumbbell placed on it. Interestingly, the LED brightness remained consistent across the 3 weights. A 10-second delay between readings confirmed proper functionality, and the LED turned on immediately upon reaching the voltage threshold. Ohm's law is used in Figure 5, which is a bar graph plotting the current measured for each dumbbell weight. The current was recorded in Figure 4. The current increases as the weight increases. Ohm's law is the current equals the voltage divided by the resistance. The resistance is 220 ohms, and the resistor value, which is the resistor value. The energy efficiency ratio is used in Figure 6, which is a line graph that shows how as the weight increases, the efficiency of energy also increases. The efficiency ratio is the energy outputted divided by the total energy of the system times 100. The total energy is 5 volts. I calculated the average voltage output for the weights. The 10-pound dumbbell produced 2.5 times the output of the 5-pound weight. While there is a linear relationship, deriving an exact formula to estimate voltage based on weight proved to be challenging. The low variation in standard deviation indicated consistent measurements, as seen by the small standard deviation and error bars on the bar graph. The second experiment supported my hypothesis, showing an inversely proportional relationship between weight displacement and produced voltage. As the weight moved further away from the center, the voltage decreased. This is supported by figures 10 and 11, which show a table and bar graph of the recorded data to help viewers visualize this trend. When the weight was placed 6 centimeters away, it produced more vibrations, leading to voltage readings close of those at 4 centimeters. The efficiency of energy, shown in figure 9, also decreases as the displacement of weight moves further away from the tile center. Similar to the first experiment, the device stabilized before delivering the expected voltage readings, and the delay between readings was consistent. The data displayed an exponential decay pattern, indicating that voltage decreased as the distance increased. There was also low variation in the dataset due to a low standard deviation and small error bars. I calculated a 95% confidence level for voltage outputs from a 10-pound dumbbell placed 4 centimeters away from the center, ranging from 1.21 to 1.33 volts. A contour plot was created as seen in Figure 8, which illustrates the voltage outputted, which is the z-axis, at different radii of the tile using the tile's dimensions, which are the x and y axis. We see that the center of the tile produces the most voltage as it's the brightest, while the outer edges of the tile produce the least amount of voltage as it's the darkest, which is again supported by the sidebar. This small-scale energy harvesting demonstration highlights how the technology can address America's overloaded power grid. With an average human weight of around 180 pounds and the potential for stronger piezo discs, this project shows the broader applications of piezoelectricity, especially for lighting, which requires more voltage than signals. My research indicates stable voltage outputs, suggesting that reliable energy for lighting systems. As people walk, Society can adapt to this energy harvesting method, showcasing piezoelectricity as sustainable alternative energy sources for lighting. While piezoelectric discs generate lower voltage than the electrical power grid, they excel at harvesting small amounts of energy from constant vibrations, making them suitable for powering individual components, such as an LED light. Piezoelectric materials generate voltage in response to applied stress. When weight is added to the center of a tile, the piezoelectric effect increases due to a greater strain and polarization at that point. However, this effect weakens as the force moves away from the center, demonstrating that piezoelectricity depends on both the magnitude and the direction of the applied force. My data suggests a solution to electricity overuse from our power grid through energy harvesting techniques. I generated enough voltage in a miniaturized setup to power an LED and plan to expand this into a full-scale household lighting experiment. By harnessing weight and movement, we could generate sufficient voltage to power light bulbs and buildings, reducing our reliance on the grid and minimizing the associated risks. So the next time you use electricity for air conditioning or charging the device, think about its impacts in the world around us. Thank you for listening.